The visible light range is only a small fraction of what is out there. It only counts for 5% of all the matters in the universe. So, what's the other 95%? They are dark matter and dark energy. In the 1960s, astronomer Farrah Rubin was observing spiral galaxies. She was interested in how they rotate, as you can learn a lot about galaxies that way. Think about the solar system. Back in the 1600s, Johannes Kepler figured out that the further a planet is from the Sun, the slower it orbits. Isaac Newton put numbers to that, calculating the strength of the Sun's gravity, which means we could in turn get Sun's mass. Same with the galaxies. If you can measure how they rotate, like how rapidly gas clouds move in their orbit near the edge of the galaxy, for example, you can calculate the mass of the entire galaxy. Galaxies are so big that you can't physically see the nebula move, but you can measure the Doppler shift, which gives you their velocity. What Rubin expected to see was that the further out from the center of the galaxy the gas cloud was, the slower it would be moving, just like more distant planets from the Sun. What she got though was the opposite. For many galaxies, the further out from the center you went, the faster the clouds were moving. Even at best, the velocities flattened out with the distance when they should have declined, which means the gravity of the galaxy was constant throughout the disk, not dropping from the center as you would expect. But that's insane, because images of galaxies show that the number of stars and other massive objects clearly got lower the further from the center you went. There simply isn't enough mass far out from the center to account for the rapid rotation rate, or not enough mass from the things we can see. The only explanation is that there must be dark materials contributing to the gravity. Not only that, the galaxy must be embedded in a halo of this material to get the shapes of the rotation graph right, and there must be a lot of it. Rubin found there must be 5 or 6 times as much of this invisible material than the visible material matter in the galaxies. We see similar behaviors in elliptic galaxies, for example. Ironically, better measurements made of galaxy clusters member velocities show they do in fact move quickly, and clusters must have dark matter in them too. So, what is dark matter? Astronomers are methodical. They list out substances that they suspected to be dark matter, and they cross them out one by one. Eventually, everything made up of normal matter like atoms, molecules, protons, electrons, and neutrons was eliminated. So, this boils down to the fact that we don't know what dark matter is. Type 1a occurs when a white dwarf increases in mass until electron degeneracy pressure can no longer sustain it against its own gravity. It collapses, undergoes a catastrophic wave of thermonuclear fusion, and explodes. The beauty of these types of supernovae is that they all occur when the mass of the white dwarfs gets to about 1.4 times of the mass of the Sun. That's the magic number when the pressure overcomes the gravity and makes the magic happen. That makes them good standard candles. Objects whose intrinsic brightness does mean the luminosity is known. Knowing that, plus measuring how bright they appear to be in the telescope, lets you calculate their distance. Then those can be compared to the supernovae redshifts, which is a different way of getting that distance. This then tells you how fast the universe is expanding on a really big scale. But the results they got didn't make sense. Time and again, the supernovae were all fainter than they were expected. It was as if the predictions based on the redshifts were all underestimating the distance to the exploding star. The astronomers did everything they could to see if they had made a mistake somehow, including like making a literal list of things that can make stars look fainter. like intergalactic dust, different chemical composition for the star that blew up, all kinds of things. But in the end, they independently came to the same conclusion. The supernovae were further away from what they expected. And that meant something truly shocking. The expansion of the universe was accelerating. Now remember, that's insane because we were expecting the expansion of space to be slowing down due to the gravity of all the matter in the universe, but instead it was speeding up. The universe is not only expanding, but the expansion is getting faster and faster every day. What could possibly cause this? We don't know. But whatever it is, acts like an energy suffusing space, pushing on the expansion. And we can't see it, so it's invisible. We already have dark matter, so it naturally got that dark energy. It seems to be a property of space itself, a tiny bit of energy in every single cubic centimeter of the universe. The amount of per cc is incredibly small, but there are lots of cubic centimeters in the universe. It adds up. We can total all the matter and energy in the universe, making a sort of budget of stuff in the cosmos. When we do, it looks like this. 95% of the stuff in the universe is made of stuff we can't directly see. So if 2/3 of the cosmic budget is made of dark energy, it must have some pretty big effects, right? We think there's enough dark energy in space to ensure the expansion will continue forever, despite the geometry. Dark energy is just too powerful and will always drive the expansion of the universe ever faster. So for now, the answer as far as we can see is yes, the universe will expand forever. Space itself is expanding. As light travels from one galaxy to the next, it fights that expansion, losing energy, just like you use up energy climbing a staircase. When light loses energy, its wavelength gets longer. That's what cosmological redshift is. The more distant the galaxy, the faster it recedes, and the more energy the light loses as it travels to us. At some distance from us, space will be expanding so quickly a galaxy in that part of the universe will be moving away from us at the speed of light. Anything further away will be swept away from us faster than light. The speed of light is the speed limit in the universe if you are traveling through space, but space itself is exempt from that rule. It can expand at whatever speed it wants. The matter in it swept along with it. When you solve the equation to calculate the distance at redshift, the distance a galaxy would have to be from us to be moving away at the speed of light is about 13.8 billion light years. We can still see galaxies that far away from us. It is because the distance is how far the galaxy is from us now. When it emitted that light, the universe was much younger and smaller, and the galaxy closer to us. It would have been about 4.5 billion light years away at the time, and the light took over 9 billion years to get back. But when the space between us and the galaxy was not expanding so quickly, so the light would keep the pace. And now, after all this time, the space between us and that galaxy means we are moving away from each other at light speed. But back then, we were close enough to see each other. For that same reason, we can see galaxies that are moving away from us faster than light. This is the end of